Okay, so I sneezed and I stopped the video by mistake. So, whoops. I'm not redoing. I'm going to continue. We will have a two-parter here because I'm not restarting that. I'm not losing another 5 minutes. Okay. So, as I was saying before I so rudely interrupted my own self, is that if we're looking at this projectile problem, the time in the air is going to be based on the y direction. Right? This is a horizontal projectile. It's a plane flying horizontally and just drops stuff. So your time in the air, figure that one out in terms of the variables, right? And remember your delta x is going to be vx times t. And we're looking for the distance. So we want to just take that velocity and we want to multiply it by our time. And there you go. You've got that one. This question, just read it carefully. It's not hard. Same thing for this one. This one, I think, honestly, I think that someone who doesn't even know physics should be able to come up with this one. Which one is going to have the greatest horizontal range? Take a look at how it's shooting and the velocities and the angles, and I think you should be able to figure that one out. And then comes this one. This one you need some assistance. So here again, here I am. All right, so come on, line this up for you. This will have to do it. Okay. Ooh, that's not what I meant to do. Okay, let's just give ourselves a blank spot. We need a really good free body diagram here. All right, now they're talking capital M. I'm going to call it M3. Just otherwise, I think we're going to get ourselves all sorts of confused. Make sure you change it as you go. This is exactly the sort of question that has been giving you guys the conniptions. Okay. Not just conniptions, the conniptions. So watch out. Okay, angle theta. All right, I think I am blocking some things here. So there we go. All right. Blocks 1 and 2 move with constant velocity down the inclined plane. Good to know. All right, I'm sorry, I blocked that a little bit. Let's try that. Down the inclined plane. The kinetic frictional force on block 1 is F, and on block 2 is 2F. Okay, so I'm just gonna, I don't even know where to put that. All right, M1, we're gonna say, nope, that's totally off the screen. Let's try this again. M1 has a friction of F. There we go. M2 has a friction of 2F. We'll need that, but I don't want to write that on my diagram. That's just going to mess things up. And all right, on the figure below, draw and label all the forces on block M1. All right, well, obviously you're not submitting that, but it would be handy to do so. So actually, I would suggest 3 free body diagrams. And then we should have one for the hanging block. All right. Before we worry about any of this stuff, let's just do this. Let's just work. Okay, and we're moving with constant velocity. If we're moving with constant velocity, the good news is we have balanced forces. That's good to know. Always start with the hanging mass. It's the simplest one. Okay, so M3G, tension. All right, now again, we're ignoring the pulley, so all the tensions are going to match. That's kind of nice. All right, we know that these are balanced forces, so those two are equal. That's the easy one. Now let's do M1 like they asked us to. All right, so we of course have gravity. We have normal force, and we have a tension force. And remember, we have, let's see, it's going down the inclined plane, right? Yes, it is. Okay, and remember, we have friction. Friction of F. So don't forget that one. Okay, this is what it should look like. Do you need to break it up into little triangles and stuff? Yes, but not on a free body diagram. Not for points. You don't want that to get in the way. Now, number 2 is the trickiest of the free body diagrams, but it's still not that hard. All right, so M2G, if you haven't tried to do this by yourself, you should. You should pause me. You should try it and then check your work. It's better for you. I know you think, no way, man. I'm going to watch you do the whole thing. But I'm telling you, it doesn't put tools in the toolbox. You got to practice. You got to get stuff wrong and then double check your answer. All right, so you've got tension going this way, but you know what? You also have tension going this way on the old block. Not only that, we've got little 2F friction between block 2 and the ramp. Hopefully you can read that. Hopefully that's big enough for you. Okay, good old free body diagram. Ta-da! Okay, now, what do we want? Coefficient of kinetic friction between the inclined plane and block number 1. All right, so let's focus then on, let's go to this, let's go to block number 1's free body diagram. So I'm going to mess mine up because I don't want to redraw everything. But again, I'm not, no, come back. There we go. I am not taking the AP exam, so I can tell you what to do and then disregard my own instructions. I admit it, I'm going to be naughty about it. All right, but tough noogies is, I think, the official term for that. All right, let's give this a try, shall we? We know. What are we looking for? Coefficient? Coefficient of friction. Dang it, that's off the page. I hate that. Move you over just a little, huh? There we go. Coefficient of friction is going to be kinetic friction divided by normal force. Okay, now we do already know the force of the friction. We know the force of the friction is F. So we really, still off the page. I was just trying to make that easier to see. All right, so I know I can put F up here, but we do need to know what the normal force is going to be on this little guy. So when we look at our arrows, normal force is going to match mg1 cosine theta. Or m1g, sorry, cosine of theta. There's your answer for the first one. That's actually a pretty easy one. All right, determine the value of the suspended mass that allows blocks 1 and 2 to move with constant velocity down the plane. That's the longest one. I might skip that one and go right to good old part D because that's fast. And since I still just want to know about block 1 anyway, let's just fix it. All right, so if I cut the tension in the rope, now what? You're going to have a net force, right? So what you would be saying here, remember I've skipped down to D. I will have a net force. Yeah, you can see that. The sum of the forces would not be 0. Let's change the color. All right, so the sum of the forces would not be 0. F equals MA. State your intentions before you do the math. Okay, so M1A equals the bigger forces minus the smaller forces. The bigger force is going down the hill. That's the way it's going to accelerate. So M1G sine of theta is going down the hill. What is trying to resist and go the opposite way, up the hill? Friction. Okay, now what am I solving for? I'm solving for A. So just divide by M1. Ta-da! See how fast that is? That's not bad. It's that middle piece. It's that middle piece that's going to be tricky. So here we go. All right. Let's remember we still have tension here. I only crossed it out for that last part of the problem, but now we're dealing with now we're going to go back to moving down the hill at a constant velocity. Okay. This is our first example where we have 3 objects in motion here. So we are going to have to use all 3 of the free body, diagrams. Here we go. All right. Now, I already wrote the first one. So, all right. Do I want blue? Probably not. Let's try purple. Let's try getting all school spirity and stuff. All right. Let's do each one. M3G equals T. That's our first one. Let's do the other one. Let's do the next one. Or I should say the middle one. Okay. Now, this guy, we haven't really talked about him, have we? There we go. All right, so trying to go down the hill. All right, we have a tension And we have m2g sine of theta. Oh, I should have written that differently. Let me erase that and line it up better. Just messed the whole darn thing up. I messed everything up. Dang it. Okay, let's try that again. I just want to line up my equal signs, you know? I just want it to look neat for y'all. That's what I'm trying to do. All right, so going down the hill, I'll just put in my equal sign first. There we go. These are the two arrows pointing down the hill. Now, what's trying to point up the hill? Well, tension and 2F. Okay, now let's do the first one. Let's do this little guy over here. I'm going to be smart and I'm going to line up my equal signs, right? So I don't go through the same nonsense. Okay, so what's trying to go down the hill? M1G sine theta. Oh, I guess that's it. Whoops. What's trying to go up the hill? Tension plus F. Okay. Okay. Let's hang on one second here, peeps. Okay. I realized I made a mistake. That's why I paused for a minute. I got to fix something. I need to write all of these equations with the same direction of motion for each. And what I mean by that is over here, I wrote the stuff trying to go down the hill. And over here, I tried to write the stuff going up the hill. And I started to do the same thing over here, and I did the same thing over here. But I did not do it for the top equation. I wasn't thinking. I just started. So I'm going to reverse this. All right, let's see if I can. All right, now I messed up some of my free body diagram, but I think we're pretty good anyhow. So I'm not going to worry about it. Now, if you're saying, wait, what? Why do we have to do that, Mrs. Grady? Well, it's because I'm trying to be consistent. I'm trying to be consistent with like what's going on here. And wait, no, I did erase something. Kind of a mess here. This is my middle guy. What did I do? I think I erased that there. It's not a 1, it's a T. There we go. The reason is because it's all going down the hill, right? So over here on the left side, on this side, that's everything trying to go down the hill. Well, when it's going down the hill, the tension is actually moving up. So I need the tension from the hanging mass to be, I need to be consistent. Otherwise, it's not going to work out. Okay. Now let's add these three lovely equations together. And let's take a look. All right, so my tensions over here, cancel these tensions over here. And then I end up with M1G sine theta plus M2G sine theta, although I erased the theta, sorry, equals M3G plus 3F. All right, that's my statement of balance. What's going on? I don't even remember what we're solving for anymore. Oh, we're solving for M3. I mean, we're calling it big M, but that's basically what we're solving. So this is what we want. We want to isolate M3. So you know what I'm going to do? I'm going to move 3F over there. It's M2G sine theta minus 3F equals M3G. And then I'm going to divide this whole congested mess by G. What's nice is that at least that will cancel. So, all right, M1 sine theta plus M2 sine theta minus 3F equals M3. This is your answer. I bet you're going to have to use a lot of parentheses, people, I have a feeling. So just be careful when you're typing that little sucker in, because you know you're doing your variables in there. I know they let you preview it, so you can double check it and see if it says what you want. All right, but again, when it comes to doing multi-body Atwood machines, free body diagram for each and every object, line them up in terms of the equations. Like I just spent 5 years doing fixing and changing, right? You're going to have three equations, whether they are of net force or balanced force, but you're going to have them lined up so that they're all going in the same direction. It's much easier when you have accelerations, because you always start with M1A, M2A, and then they're going in the proper direction, unlike balanced ones. They got to be going in the right direction. Okay? So hopefully that helps you. Those are some good questions. All right, y'all. Talk to you soon. Bye.